Dear colleagues, I want to present in my report a short overview of our investigations. Periodically, spatial periodic structures formed by the inorganic nanoparticles in polymer matrix were the subject of intensive research in recent years. The high interest to these structures is caused by the following reasons. First of all, the metal, organic, semiconductor, and other nanoparticles, which have specific physical properties as luminescence, nonlinearity, or optical gain, can serve as inorganic additives. The combination of these intrinsic properties of nanoparticles with the diffraction properties of these structures is promising for design a new generation of light-emitting and light-controlling devices. Among different methods of periodic structure formation, the holographic method is the easiest, cheap, one-step technique to obtain high-efficient structures with submicron period and large area. Photopolymerization in interference pattern is used for the obtain these structures. Usually, initial mixture for holographic patterning include monomers, photoinitiator of polymerization, and nanoparticles. Nanocomposites for holographic ordering. The investigations was initiated by Bunning and his scientific group, and were continued by another groups. Now, there are many different formulas of nanocomposites for different nanoparticles. Some propositions are based on the specially designed monomer that are not commercially available. So, the general aim of our work was to develop unified organic and inorganic nanocomposite based on commercially available acrylate monomers and suitable for production of the highly effective holographic elements. Our investigations led to the conclusion that the two-monomer composite is the most appropriate for the holographic ordering of nanoparticles. This mixture contains two monomers that must polymerize independently with different rays, and this mixture must be the good solvent for the nanoparticles. The selection of monomer composition can be summarized as follows. The optimal composition includes low reactive monomer with one double bond that forms the linear polymer chain, and the multifunctional high reactive monomer with quantity of double bonds more than 2 that forms the cross-linked polymer network. It should be noted that all these compositions are suitable for the holographic pattering, but the mixture of this monomer with one of the low reactive monomers are the most suitable for gave us the best results. The properties of nanoparticles are shown in this table. The refractive indices of nanoparticles must be larger or smaller than the refractive index of polymer matrix to provide the high contrast structure. To ensure the compatibility of inorganic particles with polymer matrix, its surfaces were covered by the organic shell. Nanoparticle surfaces were modified by long-chain fatty acids. The photopolymerizable mixture is sandwiched between two glass slides separated by the calibrated spacers and then put into the interference pattern. Diffraction formed by the two recording beams. Diffraction efficiency of the grating is measured with help of the helionium laser beam fold on the grating under the break angle. The amplitude of refractive index modulation can calculate it from the well-known Kogelnik's formula. In the periodic, special periodic recording field, the special periodic recording field initiates the polymerization of high reactive multifunctional monomer in the eliminated areas and causes the diffusion of this monomer from the dark area to illuminated ones. At the same time, the low reactive monomer and nanoparticles move into the opposite direction. After the full polymerization of both monomers, the permanent structure is formed. The amplitude of refractive index of modulation of this structure is determined by the difference between the refractive indices of polymer-rich and nanoparticle-rich areas. In this table, we offer the holographic properties of proposed nanocomposite. Refractive index of modulation, the amplitude of refractive index of modulation of refractive index, the theoretically estimated maximal possible value of this amplitude optimal concentration of nanoparticles in composite and relative modulation of nanoparticles concentration are shown in this table. As you can see, for the all cases except this silicium oxide nanoparticles, the obtained value of N1 approached to the theoretical limit. And relative modulation of concentration close to the 90%. That means that all particles are located in the one planes of the holographic gratings. In next table, we compare our results with the results obtained in other main groups. This is groups from Japan, from Netherlands, and from Air Force Laboratory of United States. As you can see, in all cases, refractive N1 for our nanocomposite exceed this parameter for the composites proposed by another groups. Now I want to show several examples of applications of such structures. We have shown that the nonlinear properties of the titanium dioxide nanoparticles causes the nonlinear response of the diffraction element. As it is known, the titanium dioxide nanocomposites are characterized by cubic nonlinearity, and taking into the account of this information and using our experimental results, the diffraction efficiency increase with increasing of the probe beam. And taking this experimental result, we have estimated the nonlinear coefficient of our nanocomposite. The calculated value coincides by the order of magnitude with obtained by another authors for the nanocomposite with chaotically distributed titanium dioxide nanoparticles in polymer matrix. It should be emphasized, the mechanism of the nonlinearity of this composite needs in further consideration. It should be emphasized that the high sensitivity of diffraction efficiency to the small changes in value of N1 is makes this nonlinear one-dimensional and two-dimensional structures perspective for the practical applications. Another, the high contrast structures obtained for the composite with metal oxide nanoparticles can be used as diffractive optical elements. Here you can see the examples of the one-dimensional gratings and the optical qualities of gratings with different thickness, 20 and 500 micrometers. And in this figure, you can see the macrostructure of two-dimensional tetragonal and hexagonal elements, and the picture of diffraction of laser and collimated light beam on these structures. Our last experiments show that the two-dimensional microstructuring of nanocomposite containing argentum nanoparticles sufficiently influence the dynamic of electron excitation in these plasmonic structures. Nanocomposite that contains high luminescent nanoparticles can be used as can be used in holographic security technologies. This composite allowed to production of the holographic element visible in the white light, as well as the observation of the green luminescence in the planes of the grating reached by the nanoparticles. This luminescent structure can serve as the additional protection level in the holographic security labels. And another application of such structures is the cavity with distributed feedback for lasers using different active materials. Semiconductor nanoparticles. Semiconductor nanoparticles can serve as the active medium and can formate the distributed feedback at the same time. We have observed the self-amplification, amplified spontaneous emissions in such system. And the last example, we fabricate the distributed feedback lasers using the zirconium dioxide nanocomposite doped with laser dye, and we observed the high efficiency lasing with narrow spectral band that can be change its wavelengths with the varying of the grating period. Finishing my report, I want to show the authors of these works. Our studies were performed in the Institute of Physics of Academy of Science of Ukraine by the Pavel Yezhov, Lyudmila Kohtich, and Dr. Tatiana Smirnova in cooperation with the scientific group of Professor Stumpe and Dr. Oksana Sakhno from the Fraunhofer Institute for Applied Polymer Research, Potsdam Goal. Thank you for your attention.
Thank you, Dr. Smirnova, for your talk. Now we have time for questions. Please.
Okay. I have a question about stability in time of the quality of these materials, and also what is the effect of temperature and humidity?
Yes, I understand. After the full polymerization of both monomers, the structure is very stable, and we now work with the grating that can be recorded 5 or 6 years ago, and our polymer is hydrophobic, and so the humidity don't.
Hydrophobic. And temperature.
And temperature for the room temperature, or when the temperature increase to the 100 degrees, it is a bad situation for our polymer gratings.
Okay. We have a question from the rest of the audience.
What is the time of hologram registration?
What?
The
The time of holographic formation is of about 1 or 2 minutes. And the hologram formed from the liquid phase to the hologram without any post-exposure treatment.
Okay. The last question?
The distribution of the nanoparticles before holographic imaging is uniform and homogeneous, as I understand. And afterwards, is it known what is afterwards?
We have bought these nanoparticles, and we have obtained these nanoparticles from different firms, and the size distribution of these particles is.
I mean the distribution within polymer. Afterwards, is it homogeneous or?
The distribution is spatially periodic.
Yeah, but of the whole substance. But
Yeah.
of the particles themselves.
Sorry.
I
So,
with nanoparticles located in the dark zones,
okay.
and polymer located in the illuminated zones.
Thank you very much.
Okay. Let's thank Dr. Smirnova once again.